Okay, so last time around we are talking about this equipotentials, right? So I told you that the equipotentials, this equipotential surfaces, and the electric fields, these are perpendicular to each other. Okay. So last time somebody asked why this is so. The explanation I gave that time was not that good. So this time I have come up with a better explanation. Okay, a simpler one. So let's say this is some. Okay, somebody else is joining. Yeah. So let me admit. Okay. Okay. So Sneha. So we are starting. Okay. Yeah, we have just started. So I was talking about why this electric fields. This is always perpendicular to the equipotential. So let's say this is some equipotential, okay. So there is on this surface the potential is some constant value. Now let's say I am so there is a positive charge. Let's say there is a positive charge, and I am moving that positive charge slightly along this curve, okay, slightly along this curve. And this small distance I call as my dl vector, okay. Now because this is a equipotential, the dv, if you calculate the potential difference between this, let's call it a point and b point. So because these are very close, I am saying that this is, I am denoting this difference of potential by dv, which is nothing but vb minus va, right? But because we are on top of a equipotential, this VB and VA are same, therefore this dV is actually 0. Now you also know that the dV is related with electric field via this equation, E dot dl, okay. So probably you know from your textbook. So there is a minus sign, and you have to take a dot product of E dot dl. So dl is the infinitesimal distance on the curve or on the surface, and dv is the potential difference between these 2 points. Okay, somebody else is joining. Let me just yeah, I think yeah, it's fine. So this dl is this distance, right? So because we are on the equipotential, this is, we can just put 0 for this thing, and we get E dot dl, okay. So this gives us that E and dl's dot product, which is nothing but E times dl cos theta, is 0, okay. So that means, okay, so here the electric field is not 0, okay, it is not arbitrarily 0. dl is not 0 also. You just saw that this is some infinitesimal distance. So the only solution to this equation is cos theta is equal to 0. So cos theta is equal to 0, that means one of the solution can be pi by 2. So what does this mean? This means that if there is an electric field in this region, then it will always be perpendicular to this dl, okay. So if you can choose this dl in this direction, the electric field will be perpendicular in this direction, okay. If you chose dl in this direction, then it will be perpendicular. So throughout, if you construct this thing like this perpendiculars to these dls, then you will see that you have obtained that this electric field is always perpendicular to the potential surface, constant potential surface, okay. So to get some more idea about this how does this electric field look and how does these equipotentials look, I will show you a demonstration, okay. So there is a very small program that I have written which will show you how this charge will look. So don't bother how the program works, but I will show you some nice plots. So let's say we have a charge, a single charge sitting at the origin, okay. So if you want to look at the equipotentials, how would it look? So you see, so let me just explain what this thing is. So these circles, the circles that you can see, these are the equipotentials, okay. These are the equipotentials of your this single charge, okay. And the charge you can see this charge at this origin that I have denoted with a this square or this diamond shape. So this means that if you have just a single charge, then the equipotentials will be just a sphere, okay? Or if you are in 2D, then the equipotentials are just a circle, okay? So on these circles throughout this the potential will be constant, okay? And the colors give you some values, okay? So you can see that the potential around the origin is quite high. It is 10, okay, around some units, okay? And as you go away, the potential actually decreases, okay? So like when you are away, like in this on this potential, then the potential is like 1 unit, okay? And also the equipotential means that if you put a particle here, then you will not have to do any work if you move the particle along that equipotential, right? Because equipotential means there is no potential difference. So this is how a single charge looks like. So let's increment this and see how double charge looks like. So I can also show you how the electric fields actually look like. So the electric fields are always pointing out, okay? So this is very much okay, so the diagram is very much congested, but if you see at some point, like look, the focus on this arrow, see, okay? So this arrow is the direction of the electric field. So you can see that this arrow is already perpendicular to this circle, okay? So yeah, so electric field and this equipotential surfaces are always perpendicular to each other. So I will show you some other diagrams also to get you a good idea, okay? So let's say I have put a charge, so let's say I have two charges which look something like this. Okay, so right. So you see what I have done here is I have put two positive charges a little bit apart, okay? So this this red diamonds, these are the position of the charges, and all these constant black lines, okay? So these black lines are what the equipotentials look like. So you see, when you are very much close to the origin, the equipotentials look somewhat like a dumbbell, okay? A dumbbell shaped equipotential. But as you go outwards, then this becomes elliptical, okay? But as you go very, very outwards, then it becomes almost like a circle, okay? So like this part looks like a arc of a circle. So why this thing is, generically this is always true, because when you are looking at the system from a very large distance, then what you see is just a single charge of twice the amount, okay? So that's why when you go outward, or the equipotentials will try to become circle or spherical in 3 dimensions, okay? So this is how two positive charges a little bit apart looks like, okay? So if you want to look at the look at the electric field also, so I have got you covered. I'll show you how this electric fields looks like also. But this is again, this is very much congested, but you can almost see that, like look at this arrow. This arrow is perpendicular to this curve, right? Are you getting my point? So what I'm trying to say is, whatever the system is, the electric potential is always intersects perpendicular to this, intersects the electric field in a perpendicular fashion. So I will show you some other things. So let's have a little fun over here, okay? So let's say I am looking into a dipole, okay? And I will not bother about looking in the electric field because these are very cumbersome, but I will show you how the equipotentials look. You see, so the equipotentials completely change, right? So when we had two similar kind of charges, then initially we had a dumbbell kind of shape, right, for the equipotential nearby this origin. But when we have these opposite charges, you see the potential is higher. So that's why it has this yellow value. The potential is higher in this region, and the potential is negative in this region. Okay, so this is something something like a dipole. Okay, this is a dipole where you have two opposite charges which are very much close. So you see that this is something like is part of a circle, but it is not a concentric circle, right? So yeah, so this is how you get some. This is how the potential of this dipole looks like. Okay, so you see that there is a straight line which goes along this intermediate region, right, which passes through x is equal to 0. Now if you try to look up the value, this value is actually 0. So on this line the potential is 0 throughout. So what does this mean? So this means that if you put a particle on any point of this thing and if you give a slight push in the y direction, then that means that the charged particle will not see any of these two charges. This will go straight away. This will not be repelled or attracted with this thing. This will go straight ahead. It will not interact with any of this. But the condition is that you will have to plug the particle at x is equal to 0, and this works for any y, any values of y. So you just put a particle here, some charged particle, positive, negative, doesn't matter, and you just give it a slight flick of your finger. Okay, so what will happen is the particle will go straight through. It will not do repulsion or interaction through this any of these particles, right? Because the potential is 0 here. Okay, so a few more figures I'll show you. So let's say we have +1. So let's say we have 4 charges, similar kind of charges. So let me quickly make those charges here. So I'll just shift the positions. Okay, well, this didn't happen. Q1, Q2, Q3, Q4. Okay, what I'm getting here? Okay, something wrong going here. Yeah, okay. I just messed up a sign. Okay, so this is some funny looking kind of shape, right? So what I have here is, so these two are positive charges, okay, and these two are negative charges, okay. So yes. So you see that there is similar kind of, this is somewhat similar like the dipole that I showed you before, but this is tilted, right? So as if there are two charges which are little bit separated, that makes this circle a little oval shaped, right? But the symmetry is still there. So by symmetry, what I mean is that there is still this zero potential line, which means that if you put any particle on this line and if you just if you give a little push, then it will just go through. It will not feel any attraction. Okay, so this kind of structure is called quadrupole. Why quadrupole? Quadro means 4. So you see there are four kind of charges. So this is some similar kind of a quadrupole. Okay. So I'll end this with some other diagram. So this will be the end, I promise. Yeah. So so here I have a, okay, not this one. I do not want this one. What I want is yeah, plus, minus. Right, yeah, this is the one I'm talking about. So you see that beautiful flower looking kind of structure. These are just potentials. These are just equipotentials. Okay, so what I have here is 2 positive charges and 2 negative charges. Okay, so two dipoles basically. See, plus minus. It is basically like 4 dipoles, right? So there are 4 charges which is making up a quadrupole. Okay, so out of these 4 charges, these 2 are the positive ones. So how can I tell? Because the potential is higher near these regions, okay, and the potential is lower near those regions. So I know that these are the negative charges, right? And these repel each other in such a way that these equipotentials become like a flower. Okay, so where the repulsion is most, you see that these flowers become squeezed, the petals become squeezed. Okay, and where the repulsion is not that much, there the flower gets some space to flourish. Okay, so here also I would ask you to look at this symmetry I was talking about. So right now there are 2 lines instead of 1 where the potential is 0. So it is this diagonal line and also this diagonal line. So on these 2 lines the potential is 0. So again, so if you just put any particle, any charged particle, positive or negative, it doesn't matter, if you just put it here and if you just give it a flick of your finger, then you will see that it just goes through. It doesn't interact with any of these things because the potential is 0. Okay, so I'll show you the electric fields of this thing also, but this is again a little bit cumbersome to look at. But anyway, let's look at it. So you see the electric field is always perpendicular to these surfaces, right? So electric field is perpendicular, and for positive charges the electric field goes outward. Okay, so you can see the arrows which are emanating from this yellow regions, which are positively charged regions, they are going outside. Okay, and as you go out, the electric field's intensity decreases, right? Because we know the electric fields of each charges reduces as 1 by r square. So as we go very outward, we see that the length of the arrow is decreasing. That means that electric field is also decreasing, and you see along these lines there is no electric field at all, right? Because there is no potential difference, there is no electric field. Okay, and for this negatively charged regions also you will see that again, so the arrows are perpendicular to the surface and the arrows are coming into this negatively charged regions. Okay, yes. So there is a terminology that we use in physics. We say that these positively charged particles are the source of the electric fields, because electric fields are as if getting outwards these positively charged regions, and the negatively charged regions, these are the sink of the electric field, because all the electric fields draw towards this negatively charged region, right? So yeah, so this is how the electric field and potentials look like. Okay, I hope with these diagrams you get some idea of how to think about it. Okay, so we have talked a lot about the equipotentials, these things. Yeah, it was a lot fun, right, to look into these diagrams. Okay, so let's look into some other problems, right? There are some other things that we need to do apart from equipotential. So let's look into this. I'll delete this part actually. Yeah, we don't need that anymore. Okay, so let's look the first problem that we'll be doing today. So first one says that so the electric field in a region of space has components Ey, Ez is equal to 0, and Ex is equal to 4 newtons per coulomb times x. Okay, point A is on y-axis at y is equal to 3 meter, and point B is on x-axis at x is equal to 4 meter. So what is the potential in difference between VB and VA? Okay, so so let's draw a very quick diagram. Okay, so what they're talking about there is a point B, point A, which is sitting on this point. Okay, so this is our point A and this is our point B, and the potentials are denoted by VA and VB on those points. Okay, and in this whole region the electric field is only along this x-axis. Okay, all the other components are 0. Very simple, right? So to calculate the potential difference between these two points, what we'll have to do is we'll have to evaluate this integral. Okay, so what this integral means, that so to the difference between VB and VA is just a line integral from A to point A to point B, and we have to calculate E dot dl. Okay, so dl will be, let's say if we choose some path like this, like the blue one that I have drawn here, then the dl will be in this direction. So this is your dl. Okay, so what we'll do here is now we'll just plug in the potential. Okay, and you can just we'll plug in the electric field, and this is very simple integration. You can just do this. Okay, you don't have to think about it, you can do this. Okay, but I want to emphasize a different way, which shows you a very simple way to rather avoid this integration. So you don't always have to do this integration. Okay, so like what I have done here is, so I have so if you do a d of x square, so d of x square, and you divide it by 2, so what you get here is you get half, you get x times dx. Okay, so this is how the derivative rules. Okay, so you see that I have written my dx dx in a way that it looks like something like dx square, and I have divided by 2 so that just I get back this x dx properly. Okay, so there is 2 before. Yeah, 2 will get cancelled. Yeah, so Okay, when you can write this integrands in these things, this is called exact differential. So these are called exact differential. Okay, so when there is exact differential, then you can think of this as if this d and these integrations are cancelling each other. Okay, that is not what is actually happening, but this is a mnemonic device that I think will help you to remember this fact. Whenever there is integration and there is d, they are colliding each other and cancelling each other. Okay, you can think it like, but this is again not mathematically correct. But yeah, this works. So what will happen is this d and this integration cancels, and what we will have here is just x, and we will plug in the values of a and b. So a is given on some on this y coordinate 0, 3, right, and b point is given on some x coordinate 4 and 0. But in our expression there is only x. So what we need is only the x component of a and b point. So a component has 0, 0x, and b component has 4. So only this b component will contribute, right? So you plug in all of these values and you get some number. Okay, so the numbers are not important. You plug in your calculator and you find at the end of the day, but the concepts are important. Okay, so I'll just try. I like to elaborate a simple point here. Let's say that you have two charges. Okay, two charges sitting at point A and point B. Okay, and I am asking you to calculate the voltage difference, the potential difference between let's say VBA, okay, which is nothing but VB minus VA. And I am asking you to calculate the potential difference between these 2 points. So as I mentioned, the only single way to do this is to calculate this integration, right? But when you are talking about integration, you will always have to think about a path, okay, because integration is always done on a path. Okay, this kind of line integration is always done on a path. So the question is, what is the path that you'd like to choose here? And the answer is that there is no unique path that you can choose. So there are infinite choices of paths that you can take, which each will give you the correct and same result. Like for example, I have drawn 3 paths over here. Okay, so like there is path 1, there is path 2, and there is path 3. Now if you calculate this potential, this integration along any of these paths, you will get the same result, and you will see that the result will only depend on these terminal values, on these values of A and values B, on these coordinates. Okay, so whenever you have this kind of a thing going on, you say that force field is a conservative force. Okay, so here we are talking about electric fields, so we are going to say that the electric field is a conservative force, or conservative field for that matter. So this the property of this conservative field is that this only depends on the these terminal points which are given here by A and B. Okay, so and I also mentioned that you don't always need to do this integration, right? You can get rid of that integration if you could write this integrand into some exact differentials. So here what I have done here is I have said, okay, my electric field has 3 components, okay, and this dl which I am writing here is also dx I hat plus dy j hat plus dz k hat. So this also has 3 components, and when I am taking a dot product, I get ex dx, ey dy, and ez ds. Now the simple thing that I am asking you can you find a function f x y z on which you take a differential, exact differential, and you will get back this this integrand. Now if you can find a function, and there are ways which you can get this function, some simple ways, then you don't need to do this integration, do this complicated kind of integration. So you can just directly write this f of x y z, whose differential will give you back this this integrand, and you can just plug in these values. So you see in this description, none of the information about the path along which we are going mattered. Okay, so yeah, that is a very important thing. Probably people miss at their first read, but yeah, try to remember this electric field, this potential difference never depends on the path on which you choose, the path of integration, whichever you choose. Okay, Okay, so let's move on to the next one. Okay, so what we have got here is a graph of the x component of the electric field as a function of x in a region of space is shown in this figure. Yeah, this figure. So I have tried to make it a little big so that you can see it. The scale of the vertical axis is set by Ex, which is given by 20 Newton per Coulomb. So Ex is some unit. Okay, so this point means that you are looking at 6. Okay, so yeah, this point means that you are looking at Ex, and this point means that you are looking at minus Ex. Yeah, denoted by the graph. Okay, so in the okay, where is the electric field? Yeah, the y and z components of the electric fields are 0 in this region. Okay, so only x component is there. If the electric potential at origin is 10 volts, what is the electric potential at x is equal to 2 meter? Okay, x is equal to 2 meter will be something like here. Okay, so let's first solve the first one. What is the potential at x is equal to 2 meter? Okay, so in the last problem we saw that to calculate this thing is we have to do this integration. Okay, now this integration, you see, this is just the area under the curve, right? So like now here what they are asking is to calculate the potential at this point x is equal to 2. So what we can do here is we can go from this origin, which is our a here, to this b point. Okay, and this integration will give us just the area of the curve. Okay, now if you know the area of the curve using some geometric formula, then you don't need to do this integration, right? Now you see what I have got here is just a simple triangle. Okay, and the triangle's area is given by just half times the height. So height is given by minus Ex times the yeah, exactly, into this the base, exactly. So yeah, so by some simplification you see that this minus and minus cancels each other, and because we are calculating the difference between a and b at the origin, I am denoting the potential at origin by V naught, right? And so I'll do some cancellation and some simplification. So this expression will give me just Ex. Okay, but I have been asked to calculate the potential at x is equal to 2, right? So what I'll do now is, there is this V naught on the left hand side, I'll bring it to the right hand side. Okay, so Ex was 20 Newton per Coulomb and V naught, so potential at origin was 10, so you just add it up. Okay, so yeah, first part is done. Let's move on to the next part. Okay, what is the greatest positive value of the electric potential for points on the x-axis for which x is between 0 and 6 meter? Okay, so now what they're asking is, what is the greatest potential you can get? Okay, what is the greatest positive potential? Yeah, so you see so here the fact that you need to remember is that there is a additional minus in the expression for the potential. Okay, so that means that if we can get a negative area, so negative area means what? Negative area means area which is below the x-axis. So you see the maximum we can get is up to this point, up to x is equal to 3. So up to only this point we can get the positive potential, right? Because this area is negative up to I mean according to the terminology, the area below the x-axis will be negative, and there is an additional minus which would make this whole thing positive, right? So only up to this point at x is equal to 3, if we calculate the potential, we can have a maximum area, right? So that's why we can expect that this will give us the greatest positive value of the electric potential. Okay, the greatest, right? So again, what I'll do here, this is again a triangle, so we'll use the area of the triangle, right? So this is right now the base is this much. Okay, so base is 3, so the height is minus Ex, and we'll just multiply with a half. Okay, right? So that is exactly what I've done here. So V3 minus V naught. So V3 is at x is equal to 3 meters. Okay, so V3 minus V naught is given by minus half. So minus was there in the formula, minus Ex, which is the height of the triangle, and the base 3, right? So you just do multiplication and simplification, you get 30 Newton per Coulomb. Okay, I am not writing this units, but yeah, keep those in mind. Okay, and I need to calculate the potential at this x is equal to 3. So again, what I'll do is I'll bring this V naught from left hand side to the right hand side, and I'll get 40. So you see, so the 40 volt is the maximum potential that we can have in this kind of electric field. Okay. And also, so just remember the fact, whenever you are in a positive electric field, then the potential that you will get out of that is negative, right? So so as you go along this thing, as you go along this x-axis, at certain point this whole negative potential will be cancelled. Okay, whole negative potential will be cancelled by the, so this whole positive potential, right, plus positive potential, whole positive potential will be cancelled at some x by this negative potential. So that is what the next question is about. Okay, so for what value of x is the electric potential 0? Okay, so they are asking up to which at which x you could calculate this potential that will give you net zero result. Okay, so we'll be a little smart about this problem, and we will try to do this with as little step as we can. Okay, so you see we already know the potential at this x is equal to 3, right? So x is equal to 3 gives us potential 40 volts. Okay, 40 volt. Now if you look, so what we have here is we just need to calculate the area of this thing, right? So what does this consist of? This consists of a triangle, right? So this is the triangle, and there is this this rectangular region, right, which we need to calculate to get the potential at some x. Okay, and we will have to evaluate that x. So what I have done here is I have calculated that region. Okay, so you see so this is the area of the triangle that I was talking about. So the area was something like this, So here, where the base was 1 unit. Okay, the height is exs, and there is half. And for this part, so because this was 4, so what I am doing is x minus 4 times the exs, right? So that will give me the area of this part also. And this thing, the summation should be equal to 40 volts, which was same as this region's electric volt, this region's electric potential, right? So that they can cancel. And what we will do is, out of this simple equation, we will try to solve the x. Okay, so yeah, you do some manipulation, you do some massaging, and you solve for this x. Okay, so you solve for x, you get some 5.5 meters. Okay, so that means that if you calculate the x around some 5.5, so around here, so the net potential that you get is 0. Okay, is this clear?
Yes, sir. Yes, sir.
Yeah. Any questions up to this point?
No, sir.
Okay, yeah, great. Okay, so yeah, we have few more minutes. So let's do one more problem. Okay, so okay, two uniformly charged infinite non-conducting planes are parallel to YZ plane and positions at x is equal to minus 50 centimeter and plus 50 centimeter. Okay, so think of these lines as a planes. Okay, you are looking directly, right? So that you are looking you are getting just the lines. Okay, so these are just the planes. Okay, and they are situated at some points minus 50 centimeters and plus 50. Charge densities of the planes are 50 nanocoulomb per meter square and 25 nanocoulomb per meter square. Okay, so two different densities are here. What is the magnitude of the potential difference between the origin and the point on x-axis at 80 centimeters? So what they are asking is to calculate the potential between these 2 points. So this is our VB, this is our VA, and we have to calculate VB minus VA. Okay, so this is the thing that they are asking for. So from the previous chapter of electric fields, you might know that this electric field just superposes, right, in these regions, and you also know the electric field due to the sheets, these planes, non-conducting planes. Okay, so what is the electric field for each of these things? So electric field is nothing but sigma by 2 epsilon 0 times some I cap, for this case I cap. Okay, so what I have here is so what I have done here is for this region, for this A point, So I have done this, applied this formula for both of these surfaces. Okay, so this is for surface 1 and this is for surface 2, right? So 50 is the this sigma, the charge density, and 25 is the charge density of the other one. Okay, you add it up. Okay, you plug into your calculator, you get some number. Okay, and the other important fact that I would like to mention also, so this uniformly charged sheets have the property that wherever you calculate the potential, or wherever you calculate this electric field, the electric field is always uniform. Okay, in this region, because you see the electric field doesn't depend on any x, y, or z. So that's it is just a constant vector. Okay, so we have obtained at EA, so we'll just add it up. Okay, and EB also we'll have to add it up properly with a some relative sign, right? So that we can take that we can take care of the fact that there is the charges are actually different. Okay. So here in the first problem, so they are positive. Why they are positive? Because the sigma 1's electric field will be in this direction, and the sigma 2, which has negative charge, will also be in this direction. Okay, so that's why they add up and give you in minus I direction, electric field minus I direction. But here the electric field for sigma 1 will be in positive direction. Okay, for the 1, and the electric field due to sigma 2 will be in the opposite direction. So that's why there is this additional minus here. Okay, so you can add them up if you like to, and you have to calculate again this integration. Now so to calculate the potential difference, you have to do this integration. But the fact is the electric field is different in these two regions. Okay, electric field is different in this region and electric field is different in this region. So what I will do here is I will try to break apart this integration into two parts. Okay, so which is only inside this these two parallel sheets. Okay, so that is going from 0 to 0.5. Okay, and the rest of the part which goes from 0.5 to the 0.8. So this is your first part and this is your second part. So we have broken this thing into two parts, right? And you will just do this integration, but there is nothing to integrate because the E doesn't depend on x, right? So you will just write this dx. So dx will be 0.5 minus 0. So you get 0.5. Here also you get 0.8 minus 0.5. So yeah, you get some things, right? And you at the end of the day you will plug all of these things and your calculator will chant some numbers for you. Okay.